So, we will continue with the external noise propagation that we are doing. Last class, remember, we said something like this: at any direction q theta, if I may call it, q theta, if I may call it q theta, right, q theta actually, if I may call it q theta, right. Oh, q theta, it can be written as I theta by I s, that was directivity index, we are trying directivity factor, and which can be written in terms of p 0 square divided by p theta square divided by p s, where p s stands for going equally in all direction. Now, p theta stands for the measured pressure along given direction. So, this is square p square divided by. Now, there is one thing, you see, I theta is actually is equals to p, all I am talking of RMS, divided by rho c theta, right. Similarly, I s should be p s square divided by rho c s. Now, we are assuming that this will remain same. There is small difference, we are neglecting the difference between the two, otherwise this also should come into picture, right. So, we are saying that these are, so this are same, that is your acoustic impedance in standard condition, and in actual air ambient normally is not very different. So, therefore, we can neglect this. So, this is how we can write it: SPL minus SP theta, SPL theta minus SPL along all direction, right. So, general equation will be written in this manner: I theta is equals to, it will be written in this manner, I theta is equals to I square, I theta is equals to I square, I theta will be a q theta s divided by q theta s into I s, that is how we will write it. So, because q theta is the directivity factor multiplied by I s by definition, because we are defining it like this. So, is equals to this q theta, if we separate out q theta, then the directivity factor, then it will be w divided by 4 pi r square, equally in all direction, and simply take log 10 log of both sides, 10 log I theta by I reference, and right hand side also you take w by w reference and take 10 log of this. This will be power level, right. 10 log w by w ref is p w l, power level, plus directivity index, because 10 log of q z theta is directivity index by definition, minus 20 log r, because r square is there, and this turns out to be 11. So, that is what we have seen. So, with distance attenuation of air, of course, we said is 7.4 f square, function of frequency, and relative humidity 10 to the power minus 8. So, at low frequency this has very little effect, at higher frequency it will have some effect, this because at low frequency, supposing it is something like 100 hertz. So, 100 square would mean actually 10 to the power 4, and this 10 to the power minus 8. So, if you are adding, this is attenuation of air in dB, this is in dB. So, say 70 dB plus 70 dB plus 10 to the power minus 4 dB multiplied by some factor, really does not make any difference. Only if it is 10 K or so, this will have some, this is the distance, this is the relative humidity, this will have some effect. That is what we have seen, right. That is what we have seen in the last class. Then we said that there will be some effect due to wind. So, if there is a wind, velocity of wind, it will have a tendency to sort of distort the spherical wave front, because the wave will propagate along this direction, I mean the sound rays will propagate along this direction. So, these are the rays. Now, since the velocity at top is higher than velocity at bottom, so this will tend to push it more compared to this, compared to this. So, you will have a net effect is a vector this vector and this vector together, it will try to bend it. So, as a result, you will get a shadow region in the windward direction of the source and somewhat amplified or more sound on the leeward side of the source. So, if your building is somewhere there, you might find that the noise level here is higher than noise level there for a tall building, for depends upon the height, because if it is not very tall, then this effect will be not very significant. So, that is what it is. So, this is one effect, but these effects are either the absorption or these are not more than 5% or so. So, we really do not quantify, but sometimes we can take into account or keep this in mind that these places possibly would require slightly higher insulation than this, but as I am saying, the dB level would not change significantly. Yeah. One is the velocity, relative difference in velocity. So, this is what it is, and sound, velocity of sound along this direction, the wave. So, naturally this will tend to distort this, and this will have this sort of a thing, and this, otherwise it would have gone like this. From point source it would have gone equally in all direction. Now, you have a higher velocity along this direction compared to somewhere at the bottom. So, this would effectively bend it, point by point. If I look at it, it will tend to bend it, bend this spherical wave front, distort it. It will no longer remain spherical, rather it will try to bend it in along this direction. So, that is what I am saying, right. So, this is one effect. The other effect is that due to layer of airs with temperature change. So, temperature change results in different densities of the air layer. So, if you have increasing temperature, rho air, right, will be lower, it will be increasing along this direction, low to high, right. And when sound travels from a denser medium to rarer medium, it bends outward. For example, from a denser medium to a, so this is denser medium, greater rho here is higher than rho here, rho 1, and this is rho 2 is greater than rho 1. So, what will happen? The sound traveling like this will travel like this, right, incident angle, and this is the incident. So, it bent outward, refraction. So, what is happening here? It will have a tendency to bend outward. So, you will have one, and the from one layer to another layer it will bend like this and go further. So, it will have a tendency to actually bend here. So, you will have more sound at the ground level and lesser sound at the, because it will have a tendency to again distort the spherical wave front in this manner. It will in this shape it will tend to bend it along this direction, and this is when the temperature is increasing along this direction. That means, this temperature is lower. So, you have a source somewhere there, ground level source not very far off from the ground level, and temperature is increasing there, which means that ground temperature is lower than the air temperature. Now, this will happen actually in somewhat in the night, because ground would have radiated big or night or later early in the morning or something of that kind, and while when ground gets heated at the end of the day, then this is temperature here is higher. So, my density actually will be decreasing temperature. So, density will be increasing. So, rho will be increasing along this direction, rho is greater than rho near ground. So, rho at the top is, so this would have other effect, the opposite effect. That means, you will have something like the opposite effect means you are going from now rarer medium to denser medium. So, sound will bend inward in this direction, and if you continuously, if it bends, so it will have a tendency to have sound shadow at the ground level, because it will have tendency to bend all over and have some relatively more sound at the top level. So, again you have a building somewhere here, you do not see it over a small range of the thickness of the air layer. It has to be somewhat tall building. Then this variation you will see, temperature variation will be significant. So, you might find that less sound in the day, peak of the day, evening, when ground has become hot, and possibly more sound somewhere up there. Similarly, it will be other around in this situation. So, these effects are not very high, but one can keep that in mind. Supposing you come across, okay, sometime in the daytime when you were analyzing, diagnosing the cause of noise or something like that, there is a noise source, so one may keep that into mind and then basically take care of this. Barrier I was talking about, and I just explained this in the last class to you, that barrier should be either close to the receiver or close to the source, because sound will diffract. Every point on the path of the wave can be treated as a source again. It tends to go, the wave actually tends to, if there is an obstacle, so therefore it will, this point itself again sound would travel in this manner, and this is the diffracted sound. So, diffracted sound also, significant diffracted sound will go along this direction, right. And if you put it at center, the diffracted sound can reach the receiver again, but if it is away, then it will also go over the head level of the receiver. So, best way is to put a barrier is either close to the source or close to the receiver, whichever is in your control. So, that is what is done in case of noise abatement in town planning. You might put the if trench, if you have high wavy traffic, might put some sort of a trench, and there are your buildings. So, might be something like sort of this, there may be a tree, or a hump that will ensure that the sound does not go. If you have nothing, then put a barrier, right. So, we can now find out roughly what should be the parameters of the barrier actually, if you are designing a barrier. So, this, if you look at this, this is your source and this is the receiver. This is the source and this is the receiver, and let me call height of the source as Hs from the ground, and this is the height of the receiver, right, height of the receiver Hr, I may call it, is something like this, Hs and Hr. So, this is the height of the receiver. If there were no barrier, it would have gone straight like this. Even if there is a barrier, it will also, direct sound will anyway pass, because it will be transmitted through this, but diffracted sound path will be something like this, right. And this could be the thickness of the wall that, or barrier that I have put in, thickness of the barrier that I have put in, let us say it is T, I call it T, barrier thickness is T. Then A is this path, B is this path, or if I put it A, I can include the thickness, but usually T is relatively small unless it is very heavy, very thick. So, usually T is small, this T is small compared to A, B, and this one itself, what you call dBr plus DSB. What is DSB? Distance of the source from the barrier, distance from the receiver from the barrier. So, otherwise you will have to take half T both the places, but usually they are small. So, this A is A plus B, and this distance I have to find out. The height of the barrier, let us say, is Hb, height of the barrier is Hb. So, this is the direct path. Some rays will be reflected back, that is not my concern, but this generally is normally direct sound shadow zone. So, nothing will reach there, but still diffracted path will be there, and this path difference between these two, if it is some multiple of the wavelength, then intensity will increase, right. So, then diffracted sound would be disturbing this or reducing down my noise. So, this can be related to what is called Fresnel's number. Path difference is A plus B minus D, and Fresnel's number is 2 delta, which is the path difference, divided by lambda, because you remember that was equals to n lambda. I said that 2 delta should be equals to multiple of lambda. So, its Fresnel's number is given by 2 delta by lambda, and empirically decibel level reduction is given by 20 log root 2 pi n. This is one of the formulae. There are some other, it is semi empirical. We understand that it is related to Fresnel's number n, right. So, it is related to 20 log under root 2 pi n divided by 10 hyperbolic, the whole thing is divided by this part. So, this is together and this is 20 log of all this plus 5 dB. So, under root 2 pi n divided by, so it is actually 20 log, right. You can write it like this, under root 2 pi n and 2 pi n, right, 10 hyperbolic, something like this, 2 pi n divided by 10 hyperbolic under root 2 pi n, and this is under root again, plus 5 dB, plus 5 dB. Sorry, this is delta dB, reduction, attenuation, this is the reduction, and small delta is path difference, which is related to n. So, that is how you can calculate out. So, this is what is given, right, this is what is given. So, this is equals to delta dB, delta dB. So, that is what it is for a situation, for some condition, because this is a semi empirical equation, as I am saying, it is valid for certain condition, and that condition is for n should be greater than 0.19 and should be less than 5.03, right, 5.03, and when the path difference will be small, if the height of the barrier is quite small, height of the barrier is quite small, or no barrier, let us say. So, 20 dB for n greater than 5.03. So, there will be hardly any delta if you have less than 0.19, effect would not be, practically would not be there, because your height is so less, the path difference is practically not there. So, this is between, this is valid, and this is greater than this, you take flatly 20 dB. So, greater than 5.03, n equals to, you take 20 dB. This is related to path difference, this is related to path difference, and obviously the wavelength or frequency of the sound that is there. So, if you look at another formula which is given in IS 4554, Indian Standard 4554, which is actually the code for noise abatement in, noise abatement generally in outside, where it, for dBr. So, let us see what is this A plus B plus D. Let us get an expression for A plus B plus D first. What is A? A, one can calculate out A from here. A is nothing but DSB plus, DSB plus HB minus HS square of both. No, so what would be A? A is equals to D, A is equals to DSB square plus HB minus HS square, right. So, A is this, what is B? B is dB, this will be now dBr. If I neglect the T, thickness is being neglected, plus now HB minus HR, receiver square to the power half, right. So, this is to the power half. So, B is like that, I can geometrically calculate out this square plus this minus this, basically this I am trying to calculate out. So, this minus this square under root of that, that is B, that is B. Small t is the thickness of the barrier, which we are neglecting. Otherwise, you take t by 2 everywhere, right, but it is small. This will be large in 50-60 meters, this will be in millimeter, centimeter. So, that is why this is large in meters and this is actually small in millimeters, but if it is sufficiently thick, then you have to take that into account, otherwise you can neglect this, right. So, what about direct path? That is my what we are calling is A plus B minus D. D is the direct path, isn't it? I am calling it A plus B minus D. D is the direct path. So, D is the direct path. Direct path is nothing but this much HS plus HS minus HR square plus all this, so this height is nothing but h s minus this height h s minus h r, that is squared up, right, plus this distance which is d s b plus d b r square, and that is equals to d square. So, that is equals to d square, d square is equals to all this. So, you can calculate out a plus b minus d, which is geometrically simple, and if you want to take t, you can take t here also, there will be small value of t there. So, you add here t to this part of the thing and square it up, but that is usually will be small, that is why we are saying we do not take it into account. So, that will give you a plus b minus d, which will be equals to delta, and then calculate 2 delta by lambda for every wavelength, and you can find out. So, that is how you can calculate out the barrier height. You can design the barrier for this, design the barrier, right. Remember, this has to be solid, if not we will see what happens, we will see it sometime later on, because it can, supposing there is a hole here, this can cause some diffraction. If there is some hole there, this can cause some diffraction. Not only that, if depending upon your source, if it is a point source, so it is fine, if it is a line source, then this length also has to be sufficiently large, otherwise in plan it can again diffract in this manner. So, the the path difference, largest path difference you should be taking, because greater than 5.03 anyway deduction is, then the diffractor sound will not reach actually, right. Least sound, sorry, you should be taking the least path difference, which will be your conservative design. Least path difference will give you conservative. Largest path difference will actually increase the delta. You want to take the least delta. So, that is how we can do the barrier design. We can do the barrier design in this manner. Now, as I said that IS code gives you an empirical formula, assuming dBr is very, very large compared to DSB, which means what? Which means this kind of a situation, which means this kind of a situation, which means this situation. This is very large compared to source to barrier is small, barrier to the receiver is large. So, in such cases, formula becomes somewhat empirical formula you can use, one can use empirical formula, which may be the case in many cases, and it also assume this is much greater than source to the barrier, and this is much larger than the height of the barrier, and these are empirical equations. Therefore, it gives you delta is equals to 10 log 20 h square by lambda dsb, simple 20 h square lambda dsb. You perhaps cannot derive that out from the previous curve, it is not, but it is a separate one, neglect all those, maybe some idea you get that delta now it will be different actually. So, for this large ones, this is because the diffracted path will actually move away. So, this will be in our previous case will be 20 dB, previous case possibly it will go to 20 dB, if we calculate out the path difference, because basically this is for case that we talked about. So, but this is generally one can use this quite, there is more general, you have sort of curves plotted actually, and from that they have derived this equation. So, one can actually derive barrier design, one can do using this. That means, first you will calculate out how much is a LP you will calculate out in terms of LW plus DI minus 20 log R minus 11. Now, you put a barrier, there will be additional. So, subtract it from delta, that will be the actual LP, that will be the actual LP, right, that will be the actual LP, okay, that will be the actual LP. So, that is how one can calculate it. That means, this is additional reduction over and above what you would have got otherwise, additional reduction, right. So, if you have trees, then 30.5 dB, 30.5 meter of dense wood, but it has to be, can reduce order of 30 dB. So, this is from practice understandable, thick forest, thick wood would reduce down the noise level, thick, not really sparse, not so dense. So, about 30-meter width. So, here 30-meter width you have provided, 30-meter width, 30 point around this order, and this is your traffic source and all that. These are your residences, I mean, building, etc., etc. Then you will get it provided it's a dense forest, if it is dense forest. Otherwise, 30 dB you won't get. So, this is approximate. There are some other books will give you some other values. Many places you might get it. So, what is my strategy then? First strategy is I'd like to maintain large distance between source and receiver. That itself will reduce down the noise. Then there is another concept is that avoid the source of directional sound. For example, if you have industries here, and the windward direction also, then residences should be somewhere here if the direction of wind is like this. So, this is industry, and if the prevailing wind direction is this direction, industry should be there rather than this place. So, this is your urban area should be here, right. It is not other way around. So, that directional, or if you can put some buffer in between. For example, you may have trees here, green areas. If it is industry, of course, there is segregation of zoning. Zoning is done in urban planning. It is done for various purposes, noise, fire, etc., etc. So, in case of noise, keep the source away from the receiver. That is the fundamental. If you can't, or you do it as much as possible in urban planning, you can definitely do it, but you might put a buffer in between to enhance. For example, trees will act as a buffer, trees will act like buffers. So, you can put in buffers, right, buffer which will actually absorb the noise. Now, even within a building you can do that kind of thing. The noise sensitive, for example, a classroom, do not keep it close to the workshop, right, and if you want to keep it, say a canteen which is noisy, and classroom which is also can generate noise for other classroom. So, between two classroom there should be either insulation or something, right. Now, if you know the direction of the sound, you can keep that side away. For example, you keep it in such a manner, say the back side of the classroom might be facing where the noise, it will be blocking the noise, facing some noisy area. If the directional noise is there, something is generating, some laboratory which is actually generating noise. So, you may have to keep this, in that manner. So, this is one thing. So, that is what we mean by avoiding source of direction. Do not keep too many windows along the highway direction, right. Well, if you do it, you have to have a barrier. I mean, you have all options possible. So, this is another option. Screening by barrier, planning using non-noise sensitive parts. That is what I said, keep the non-noise sensitive parts, because some spaces are not noise sensitive, right. Some spaces are not noise sensitive, do not bother. For example, like your things like washroom, etc., etc. These are not noise sensitive, and some of them even do not generate noise and not noise sensitive. They are very good buffers, because they are not sensitive to noise, right. So, you can put in those ones which are not noise sensitive, but also do not generate noise, they are best. So, that is what it is. So, you can do that kind of planning both inside the building as well as outside of the building as a barrier. Okay. Positioning opening away from noise sources in the building. So, do not keep your windows towards the traffic side. Noise, then of course, you can do the insulation. Make the wall such that it does not allow noise to come in. How we do it, we will see it later on. So, I think that is essentially related to external noise protection, right. More of it will come back again after looking at the internal noise part of it.